welcome to our Dell'Iac seminar series. It's an honor for me to introduce a well-known professor of clear international scientific fame, Professor Yuri Ascher. At this moment, he is an invited visiting professor at Dell'Iac placed in Bari. And I take this opportunity to thank Professor Ascher for accepting our invitation to take a seminar in our series. Professor Ascher is a professor emeritus in the Department of Computer Science at the University of British Columbia. He is a fellow of the Royal Society of Canada, a STEM fellow, and a recipient of the Canadian Applied and Industrial Mathematics Society Research Prize. His research interests are in scientific and computing methods for differential equations with the constraints, continuous optimization, inverse problems, and applications including computer graphics, data science, and image processing. He has been a co-author of many scientific papers and of 4 books. Some of them can be considered milestones in the numerical analysis field. Well, now I leave the floor to Professor Ascher. The title of the talk is Wrong Numerical Solution for Dynamical Differential Systems. Please, Professor Ascher, and thank you again.
Thank you very much. It is very nice to be here and to talk in this unusual format for me. Let me see if, oh, all right, I got this. Can everybody see the?
Full screen.
Full screen, okay.
Here.
Here.
Okay. There it is with the title. Yeah, who wants wrong numerical solutions? You know, you can look at the paper of today and you'll find many wrong solutions right away. But we are mathematicians. We are trying to be responsible for what we are doing. And we want to make sure that we don't get wrong solutions. And in particular, in situations which is not like a programming error or something really silly. You know, something subtle happens that causes computation which is wrong. We would like to know those things in order not to fall into such a trap. Yeah. So I don't know how to say subtle in subtle. Is it possible? Subtle? Yeah. So I'm looking at subtle reasons for computations that come out wrong. Yeah. And there are 2 types of wrong solutions that are subtle. One that is obvious. Once you have it, you know it's wrong. Maybe blew up or something like this, or looks completely unphysical. And the other one, even more dangerous. It looks okay, but it is still wrong. In this case, you know, we may not know even that it is wrong. So, I'm going to show you, first of all, 2 classical examples from partial differential equations. You imagine that some people have seen these before. Then I will talk about situations where a particular method called implicit midpoint can come up with suddenly with unreasonable answers because of something that I will call ghost ODE. And then half of the talk will be in the context of computer graphics simulations, where again such fractional step methods that we use can yield surprises that we don't want. That's the plan for the day. So the quintessential slide is right here in front of you. I don't think I can. Oh yes, I can. I can at least here. Point at it. So this is the complex plane, real and imaginary, and these are eigenvalues, the black points. And a stable initial value problem, dynamical system, would be a safe one would be when I can draw a little circle around each of the eigenvalues of the system, and it is still in the negative left half plane. But if the eigenvalue is imaginary, like here, then I cannot do that. And that is marginally stable. You get a marginally stable. I'm going like this, but I should go like this, I guess. Marginally stable dynamical system, yeah, and that can have results, especially when you have lots of time steps in your method, because the little errors that you make in each time for each subinterval, they accumulate, and the particular error doesn't get damped, and therefore they accumulate faster in such limit stability situations. So there have been, how do I get rid of this? No. There have been two common wisdoms used in practice. One of them use a numerical method that applies a little dissipation, so that when the little errors add up, you see only the last ones, so to speak, because everybody else has already been dissipated. And then common wisdom 2 says the opposite. Don't do that, because the problems that have this, like Hamiltonian ODEs and PDEs and hyperbolic type PDEs, they have conservation properties, and you want to retain the conservation properties. Yeah? So these are two opposing common wisdoms. Okay. The second one says you can get more if you live dangerously, essentially. That's what it says. Yeah. So here's a classical example, the KdV equation. This is partial du dt is equal to coefficient beta times 2u times du dx, the nonlinear part, plus another coefficient nu times the third derivative in space x. Okay, and initial conditions and periodic boundary conditions. And we look at the difference method for that with delta x, the space interval, and delta t, the time step. Yeah. And this has been looked at for a long time. Here is a method from 1965, but by two great applied mathematicians, and they suggested an explicit scheme. So we know the solution at time level n-1 and at time level n, and we are looking for the solutions at the unknown level n+1. And so it's given here, everything here is known because it is at time level n and n-1. So here you have an approximation for u divided by 3 here times du dx, and this is the third derivative of u, discretized. And you can do a stability analysis like CFL condition, for those of you who heard of it. And it says that if you take this u to be constant, a maximum value of the constant, then the time step should be less than this expression in the spatial step, and then it's stable. Okay, that's the condition for stability. So we run it, and for this problem in particular, and try different delta t and delta x, and it blows up. And it's not just blowing up immediately like it will in forward Euler when you take a large step. No, it blows up. First of all, for t equal 1, the solution looks perfect. But for t more than about 7, it blows up. So that is a subtle reason there. It doesn't happen right away. It happens, I think that the Zabusky and Kroskal, who were great mathematicians, never saw it because they wrote a paper in 1965 and there were no computers to compute so many time steps. And so the reason is because all these little errors, especially in Roundoff, show up, they accumulate. And when they accumulate, the solution grows. And eventually it hits such a value that this condition is no longer satisfied, and then it blows up. Point is, it is a subtle reason. People did not see it for a long time. The KTV solution in this example is a soliton. It's actually fun to watch it. So it's a function of x and time. Yeah, and you can see the same sort of soliton moving unchanged in shape, just moving. And then when it hits the boundary condition, from this value is the same as this value. It continues. Yeah. And there's another soliton here, and the pretty thing here is that when the soliton meet, then afterwards they separate again. No, they don't pollute one another, the two signals. That was not calculated by the bad method. It was calculated by a good method, the solution. Yeah. So the second example, again very classical, is the nonlinear Schrödinger equation in one space dimension. So this is in the complex plane. I is the square root of -1, and the time derivative. I don't know how to make this function quiet. Sorry. The time derivative for psi is I times the second derivative in x plus this nonlinear term. And like in the KDV case, there is a norm preservation in time, and also Hamiltonian is conserved because it is autonomous. And here you can see that if one of these terms was not there, it would be easy to solve. Right? If the nonlinear term is not there, then I have a linear constant coefficient problem, no problem. And then if this guy is not there, then it is an ODE for each x. So it is natural to do a splitting method. You solve with one, and then the other, and one, and then. And so for the UDT equal to I UXX, just 3-point formula, and midpoint, it is symplectic, for those who know what it means, the norm preserving. And it's very easy to solve. And for the nonlinear guy, now for each x, it is just an ODE, and in fact, we know the solution here. There it is, so written on the slide. And so when we compose them, that actually gives us a symplectic conservative method. Symplectic means conservation of quite a few properties. I don't want to get into details there. So once again, we run it, and we take time step and space step equal, and you can see that the error in the Hamiltonian behaves very nicely. It goes down by 4 orders of magnitude, but it is a square, so it is second order method. Yeah. And the norm is fine too. The error norm is fine as well. So everything looked great. So we now, this is for t equal 200. So for delta t 0.01, you're talking already about 10,000 steps. Yeah? But if you now take even more steps, so that's the good guy, soliton again. But at t equal 1,000, suddenly once again, something goes wrong. Okay, some very small errors add up. And here, what you have, this is psi, the norm of psi. Here, this is heavy blue here, because the derivative oscillates, the derivative blows up. That's what this describes. Okay. And this is, when we calculate the error in the Hamiltonian, you can see that it's not a good solution. But once again, I actually happen to know one of the best applied mathematicians today, who was looking at this nonlinear Schrödinger, did not know that such a phenomenon exists. It never occurred to him to apply so many steps. So you can do that. This is not new stuff, in fact. You can do a Fourier transform instead of implicit midpoint. And here is the shortest MATLAB program for a PDE that I've ever seen. But the same phenomenon occurs. So your basis functions now are smoother but more powerful with the spectral method. That means that it will be more accurate when it is accurate, less accurate when it's not accurate. So once the instability sets in, it looks even worse. And here it was possible to have theory already in 1986 in a paper not many people knew about. that if you take the time step to be really small, like delta x squared, then you're okay. Otherwise, no guarantee. So here it is with delta t equal to delta x. That's a wrong solution, obviously. And here it is when delta t is small enough. Of course, now you may want to wonder whether it's worthwhile to use this method at all, because suddenly you need to take time step very small. But that's beyond the point of this talk. So these are two examples, classical examples. People have analyzed them many times. I actually spent time on it as well many years ago. And it's fun to do, okay? But it is a little bit like this picture, I don't know if you can see it, a picture that was taken in some holiday village on the beach in Brazil. And it is kind of perfect until you get back home, and then there's work to be done. And then you ask yourself, what is it that I learned from these two examples? I mean, they look like a kind of Monaco and San Marino. They don't give you the good explanation of what's going on in Europe these days. Yeah. So, so let's look at something kind of more, something else. Yeah. Does this occur at all in problems that are not these two particular ones? So let's look at initial value ODEs, ordinary differential equations. Epsilon here denotes that it is a stiff problem. Epsilon is always positive and much smaller than 1. All epsilons are like that. And initial value problem, and you assume that this problem is stable as an initial value problem. Okay. And the classical approach here is to discretize for step sizes h much greater than epsilon. H was delta t before, and now it is h because there's no delta x. And people said, let's use damping methods, okay, L stable, like backward Euler. So the derivative with u is, and then you have just g here, it's sampled at the unknown u sub n, at the unknown u sub n. Okay. So, there are higher order methods, BDF methods, and collocation at Gaussian point, not at Gaussian points, sorry, I'm here, at collocation at radar points, okay, that have the same behavior. But there are some reasons to also look at symmetric methods, sometimes, for example, for boundary value problems, okay, and other reasons too. So the midpoint method, here it is. I mentioned it before, but here it is. G is now sampled as the average of the known un minus 1 and the unknown un. Okay, that's midpoint. And then there's also collocation and Gaussian points, which are methods of a higher order of the same type as implicit midpoint. So the question is, what about this midpoint method? Is it always stable? The answer is, if it's constant coefficient problem, yes, there is something called A-stability, and that's exactly what it says. A-stability says that you give a stable method for constant coefficient problems, for any step size h. But in fact, in principle, there can be wrong solutions in the more general case. So this is the case where it doesn't happen in constant coefficients, but it does happen in nonlinear problems, and also if time variable. So here it is for time variable. It's linear problem, but A depends on T. If A doesn't depend on T, no problem. But if A depends on T, there can be a problem. Okay. So here is the method. Once again, discretization of U, and here this is the U itself. Okay, like this equation, and now here's the trick, crisis trick. It says instead of looking at the sequence U0, U1, UN, let's look at V0, V1, Vn, where Vj is -1 to the power j, Uj. Try to absorb the oscillation in this way. So what we're going to have here is canceling -1 to the power n minus 1. We're going to get a plus here instead of a minus, because this guy will have another minus. And likewise here, it will become a minus here. If I gave you 1 minute, you will be able to prove to yourself that this is true. So you see, this looks like a different approximation to a different problem, but the v's and the u's, they're either bounded or they're unbounded. It's not possible that one is bounded and the other one is unbounded. You see, so I can look at v, and if the problem for v is unstable, then I'm in trouble. So not I'm in trouble, the midpoint method is in trouble. So divide here by 2, divide here by h, organized, and you get alpha equal h squared over 4 epsilon. And now we let h go to 0 and epsilon go to 0 in such a way that alpha is constant. Okay. And this is the limit ODE that you get. The question is the initial value problem for this ODE stable? And that is not guaranteed. That is not part of this game. It's not part of the definition of the problem. You see? So the question is, how does it occur and how often? And the answer is, it does occur, but not very often, fortunately. So that's old work of mine. So I actually showed that that with DAE's differential equation with algebraic constraints, it can happen. And then with Sebastian Reichen, we actually show that. I want to show you what we show there, because I'm doing something wrong here. Moving the, yeah. So this is the simplest oscillator, except that the frequency omega here depends on time. Okay, so the Hamiltonian is not constant, but the adiabatic invariant, which is Hamiltonian over omega, is almost constant. It varies by order epsilon only. So if we look at epsilon very small, it is almost constant. So we can apply midpoint method and see how well this equation is satisfied. And the answer is it depends only on alpha. I'm not going to show you it, but believe me, this means that unless h is actually of the order of epsilon and not square root of epsilon, then you're going to get a solution that looks correct except that it's wrong. So this is a subtly wrong solution that you can get here. So that's kind of messier than those two examples of these. Excuse me. So now, let me devote the rest of this talk to something that is of more current interest to me and wilder as well in terms of mathematical understanding and concepts. And that's a problem that occurs a lot in computer graphics, especially in computer animation, and also in robotics and control and fabrication in a variety of situations. You have a deformable object like this. Well, here we also had one. This was once a beam and somebody twisted it. And here we have bending of the beam. So how do we approach this at all in terms of oh well, you took it over. Yeah. So here is an example of a simulation. Okay. And so this is a method that we had. Oh, that's great. So I wanted to say one more word. How do we get such simulations? Okay. So there is in this case, tetrahedral mesh that approximates the domain. Okay, right here, the left side. And now when you move it, the unknowns are the nodes of the mesh. Okay, they are moving. Okay, as in the second plot here. And once you organize those nodes, you can beautify the result. That's what you see here. Okay, And the equations that are solved are Newton's second law of motion. Masses times accelerations equal to forces. So Q are those nodes of the tetrahedral mesh. V are their derivative in terms of time, velocities. And masses times velocities are the forces. The forces are the interesting guys here. There's elastic force, the most important in some sense. It is the gradient of an energy, of a potential. And the damping forces are, because you know, my shirt is damp, it doesn't sort of fly around. And the damping are minus d of q, depending on usually only on q, on the positions, times v. So if q is fixed, it's linear. Otherwise, it's a non-linear expression. Do something if you want me to slow down. Okay, so then this is just gravity, no problem. Constraint is problem, so these forces of constraint arise when you have constraints. This is just the usual Lagrange multiplier notation. That doesn't mean it's not difficult, but it is kind of, in some mathematical sense, understood. So again, we have the elastodynamics equations. We actually discretize them in variational form, okay, and using a finite element method, and then that gives us in time a very large system of ODEs. The tree that I showed you moving has 200,000 unknowns. And when you do applications, for example, you have an animator trying to create a movie for Walt Disney. They want to draw every 1,000th frame, and then the physics is supposed to complete in between. They talk about 100 times more, you know, more resolution easily. They can have huge problems in this way to solve. And the kind of fundamental matrix that appears here is the tangent stiffness matrix, and that is the Jacobian of the elastic forces, which is the Hessian of the potential, and it's a symmetric non-negative matrix, not just any matrix, but has a structure. And now we just write it as a first order system instead of a second order system by writing it for both velocities and, both positions q and velocities v, and highlight that matrix K and the matrix D, which comes in the damping forces. Yeah. And the rest of it, you know, we call R hat. We don't want to care about that right now. These are the main guys. Okay. And it turns out that this stiffness matrix can have very, very large eigenvalues, frequencies, and corresponding to them, you're going to have a high frequency modes because it's in the second derivative. And so we don't like this highly oscillatory stiffness. In fact, it's hard to deal with. Fortunately, our vision system is restricted in a natural way. We don't see high frequencies. Okay, so when we want to approximate it in terms of vision, we want to damp those components rather than reproduce them. That's a major. That's why this stuff works in computer graphics. In fact, this fact. Okay, so we have a stiff problem. We must use an implicit method, not explicit, for discretizing this. And just to add misery, the forces are nonlinear, because Hooke's law, which is a linear force, it doesn't generate interesting animations. It's kind of lethargic. Yeah. So you want nonlinear, non-Hookean, neo-Hookean, yeah, or others. There have been many proposed by applied mathematicians. The first ones. This is something that only computer graphics people understand, and so on. Yeah. Many different options have been looked at. Then the damping forces. Usually people use Rayleigh force. Okay, the Rayleigh force is this combination with two parameters that we have to determine of mass and stiffness matrix times V. So this was called D before, big D. Yeah. And the question is what parameters? And in fact, what you have here is something that we are not used to as mathematicians. We actually have to model the problem and the method kind of at the same time almost. Yeah. As opposed to here is the problem, now solve it somehow. So, discretizations, one thing that comes to mind is backward Euler. Remember, we need an implicit one because it is L stable. Because it is L stable, it is, and then we have conservative methods. For example, midpoint, once again, implicit midpoint. Trapezoidal will be half of G of UN plus G of UN minus 1. And they are astable, but not L stable. They are astable, so that means they're stable for constant coefficient, but not L stable, which means that high frequency modes are damped. And then there's a combination that says, first take, this is popular in computer graphics, in fact, do a trapezoidal on half a step, and then use that for a BDF2 kind of method. For a BDF2 kind of method. So you get a second order method and an L stable method, but you do have that first trapezoidal mesh. So here comes a slide that I'm going to skip. Okay. Aha. So this is an exponential method. Basically what you have is a ball sort of moving the sheet. You have to concentrate on the sheet, not on the ball. Okay. So three motions, all of them are plausible in some way. I think that the exponential is best in this case because the implicit midpoint looks like crazy and the backward Euler looks kind of lethargic. Yeah. But they're all legitimate results, if you wish, depending on the context and what you want. Okay, all that is past. There was a volume that in fact Fasmo edited, and there was a paper that we put there about this. But now let's look at contact and friction constraints. Okay. So if I have an airplane landing, then I have an inequality constraint as long as it's in the air, which means the height is non-negative, and then when it touches, that's an equality constraint that it touched. Same thing exactly if I go like this, you know, in plane motion, these are soft objects, and when they touch, you know, there's the contact made, and remember they are described by meshes, and so you have to make sure that there's not interpenetration of the meshes. Okay, and this is there's algorithms well known, not trivial. Continuous collision detection algorithm for that. And so it is generally a DAI, differential equation with algebraic inequalities, and becomes a DAE, equalities once you have the fingers touching. So in this case, penalty methods, usually I hate penalty methods for DAEs, but in this case, penalty methods seem to be a natural thing to use, because you don't know when your DAE starts. It's not that you have DAE everywhere, like we are used to if you are from my clan. But suddenly it becomes a DAE. Yeah? So use some sort of penalty method for describing the situation. And you cannot use the semi-implicit method anymore. Semi-implicit is use one step of Euler, of Newton's method for the nonlinear equations. When you have constraints, these things often does not work well. You have to solve a system of nonlinear equations at each step, at each time step. It becomes a big problem, in fact. So there are two papers here that I mentioned. Lee and many of his collaborators, half of them are supervisors, from 2020 and another one from 2020. They use different methods. I want to show you more or less what Lee has done. So here is a penalty function, function B. Delta basically specifies how quickly you get the constraint, and or close to you get the constraint, and this kappa is 1 over delta times the material properties. And so we apply this penalty method for each of the points that touch when we get touching, and sum them up, and that is the constraint energy. Okay, and then taking the gradient of that, you get the constraint force. So now we have to solve these nonlinear equations. R of v velocity at so this mass times the difference of the v's equal to forces. So this is backward Euler, so they are sampled at Qn and Vn, the unknowns. Okay. But in the case where we have only the elastic force important and the constraint force and the contact force, okay, these are both integrable. These are both derivatives of energies. So Lee and his many friends said, what that means is that we can look at the minimization of this function phi. Okay. The gradient of that is obviously what's written here. And the gradient of that is obviously what's written here. So we have a function phi, which is one degree smoother than r, okay, where r is the gradient of phi. Okay, and so solving r equals 0 is finding a minimum for phi. And phi, because it is simpler than, for example, taking the norm of r. You can do it with the norm of r also. Minimize the norm of r, that will give you r equals 0. But here it is more natural, and you don't you gain smoothness. That's important here. So that's the optimization approach. Okay, optimization approach. And so again, the other thing is that R, the Jacobian of R, is the Hessian of this phi. Therefore, it is not just any matrix, it is symmetric positive semi-definite. So you have structure. Okay. So also, the funny thing is backward Euler, remember, is the guy that introduces a lot of dissipation. Yeah. So suddenly you have dissipation that is taken care of in an integrable fashion. This is something that I have not completely analyzed even for myself. How does it happen that this part of the dissipation force is done in an integrable way? But there's a but. The but is that not all forces look integrable. Okay, so how about friction a la Rayleigh? That is not integrable. Worse, there is also friction forces. Okay, so this is what we concentrated on, friction forces. Okay, and for them, Lee and co-authors said, oh, let's just take Qn minus 1 rather than Qn in, for example, d of Qn minus 1 times Vn, and so suddenly it is linear in Vn. There's no problem to solve the nonlinear problem. And likewise for the friction. Just look at Qn minus 1 rather than Qn, because these are not very stiff forces. That's the reason. The question is, can we get away with that? Or is there a possibility of getting wrong solutions if we do that sort of lagged friction, for example? So if you look at this guy holding a glass in his hand, I don't know if you can see that even. So this is not a glass, it's actually a cheap cup, because it's in a kind of iffy neighborhood. And there's a drink there. So if I press too much, if I press this cup too much, it will implode. And if I press it too little, then it will fall. And so suddenly you need accuracy. It's not just that it should look beautiful, you have to have accuracy here, you see. And so if you're not careful, you can get wrong solutions. Sorry?
It's okay.
So this Coulomb force, you have to be careful with how you approximate it. The full Coulomb force is in inclusion. Nobody dares to do inclusions in practice. It's too much. But the penalty function solves that, optimates that. But the point is, you cannot apply that optimization approach without a lagged friction contact. You see? So the question is, do we get away with it or not? So now we're supposed to see a video. There it is. Okay. So that's a video that we submitted with the paper, and so it has some explanations. So what we're going to look first at is grasping with 3 robot fingers, soft fingers, in inverted plates, and trying to pick it up and hold it. Okay. So that is our method, which is not using this lagged friction. And here is the method that does use it with a much smaller step size. And you will see that eventually it drops it. Okay, so you can get wrong solution kind of, if you're not, if you I don't, so this stuff, the IPC thing is their program. They put their program on GitHub, and all we did was to use the program. And it fails. I don't know why. I know why it should fail in trapezoidal, but not so badly as this. I don't understand that. So this video goes on, this is just bragging here, to do other things. We use inexact Newton, and here the question is to avoid loss of volume. Okay. For this, so this is a different question. And also 2 real-world examples. Okay, so what you're going to see is our results dressed, and they look quite like the real thing. So this is Sinner hitting a ball against the wall. And I was told this over lunch that I shouldn't say Djokovic, I should say Sinner. And this I think is the hardest example we have. Inflated tires, or not inflated tire, with friction. Okay. In this case, here's another video. In the case of this video, the approximation method, the optimization method worked well. So it doesn't have to happen. The wrong solution doesn't have to happen all the time. The essential reason, so you see a lot of friction there, but it is not like suddenly you need much more accuracy or anything like that. So, yeah. I think I'm running out of time, or am I fast? I don't know. Does anybody have an idea if I have more time? Let me say then. So one thing that has always bothered me, this is an open thing, kind of a remark. You take a differential equation, you add the penalty method. Why would that be stable? You have to sort of make sure that it's stable. Is it always stable, the penalty method that I showed you? And the answer is not quite. But the instability is not so bad. Yeah. So here's the trapezoidal rule, and we take the step size smaller and smaller and smaller. And when we get it really small, you see, you still have these perturbations because of little instabilities. The instabilities are in the second derivative, not first derivative. Yeah. Whereas, once again, this backward order is the black slave method, yeah. But here it shines once again, because for you know, h 0.004, you actually get an excellent representation of the real solution because it damps the errors, and damps the little errors. Also something that you don't necessarily, maybe you don't always, cannot always count on, but it can happen. So, just to conclude, clearly wrong solutions that again, subtle reason, but it looks bad, and then subtle reason, and it looks, and it is nonetheless, it doesn't look bad, but it is bad. And I showed you examples of KDV method problem, nonlinear Schrödinger, stiff ODEs, and Hamiltonian systems, implicit midpoint, and then constrained deformable object motion, which is a problem that many graphics people are interested, and robotics people are interested these very days. Thank you very much.
Or comments? Okay, just a moment. Okay, I see a question from Giuliana Ramella. May a similar PD model be used to describe bio-inspired systems, for instance, in image processing applications?
Sorry, I didn't quite get that. What part of the talk? So this is about the graphics, yeah? I didn't quite get the question.
We didn't get the question.
Okay, sorry. Okay. Can a similar PD model be used to describe bio-inspired systems, for instance, in image processing applications?
I'm not sure. So you're talking about the computer graphics stuff, yeah?
Yes.
So it's not just graphics, it is robotics, and it has different applications and different desire of precision. I'm somehow not able to zoom in on this question, I'm afraid.
If we have some question,
I don't know if Giuliana can specify.
Yeah. I'm not sure how to answer this, actually. Somehow it seems that technology is beating us.
I make just a question. For non-autonomous systems, you have shown us an example in which we have a non-autonomous system. Is it a problem? We can avoid this wrong solution with a suitable treatment of the time variable. I saw that you used T star, that was like an average.
Yes. Okay.
Is there an optimal way?
Yes.
In order to
Okay. Now I understand the question. So the only reason why I use the non-autonomous example is because it is a better representation of a nonlinear problem. Nonlinear problem usually arises in practice. And of course, if you think about linearizing and solving, method, each one of those depends on the solution, and therefore it is a non-autonomous. And that's why, in principle, just to look at autonomous linear problems is not sufficient. Okay. Now, there are many people in applications for whom linear means constant coefficients. Okay, so I think from this comes the confusion. I think that in practice, there are probably not so many examples where you really have non-autonomous linear problems. They're just kind of along the way for the nonlinear problems. Yeah, but the examples that I showed there in particular, the work with Reich, we actually solved in the same paper quite a few nonlinear problems with similar bad results. Okay, the only one we could prove was that one I showed, but it was typical of bad results that we obtain when you have symplectic methods that are used for step size that are not small enough. That was the essential point there.
Okay, Professor Ascher, I have a question for you. What about the pitfalls of using diagonally implicit methods, Runge-Gupta, and in particular the trapezoidal BDF2 you mentioned in your presentation? Thank you.
Yeah. So there are situations where these methods produce very nice, more interesting animations. But I wanted to also mention that they can go wrong, and that is again one of those. It's another example of wrong solution that I have not mentioned. Maybe I can go to that slide that I jumped over very quickly. Yeah, so the TR-BDF2 is one example of this diagonally implicit Runge-Gupta method, where first of all you calculate mid-step U gamma at some gamma, and in the case of TR-BDF2 gamma is 1/2, and then apply a BDF2 type thing. And so the whole result is L stable. However, the first step is just, the first stage is just A stable. So when this works well, it's very nice. And I have actually an example somewhere that shows some very nice animation using this method. But you can also have problems if it is not sufficient to have an A-stable method even in the first stage. And here is one example of that sort. If you look at the system dv dt equal to minus 1000 v and dw dt equal to log v, then and v0 is 1, and you take step size 0.1, which you should be able to do because we're looking at h much greater than epsilon. Yeah? Then this v will become negative, and then you cannot calculate it here. You can have wrong solutions that arise in this case as well. And the essential argument, the essential conclusion is that these methods are not as reliable as BDF methods in practice. Yeah. There was a talk in MATLAB of using them instead of BDF for their general purpose stiff code. And Lina Petron and I had a chat with Clive Moller many years ago and convinced him that there is a reason why not to do that. Yeah. One more question.
Other question or comments?
Yeah, I have one
Okay.
about the friction modeling. So my question is, could like some different description of the friction modeling, for example, with discontinuous system and with event detection, mitigate the wrong behaviors? Because, for example, it happens that when you it could be that the regularized model could be responsible for the wrong solution, not just the numerical method. Or thank you.
All right, that's a great question. I wish I had an answer. Friction modeling is in this context is an open. Again, not just graphics, it's robotics as well. It's an open problem, as far as I know. That's the hardest one to do. And it's not coincidence. It's that there we could actually show examples where it works and where it doesn't work, and so on. Yeah. So there's more work to be done. And there's, in the tire that I showed, another variation of the force was used to get that result. So this is in a paper which is in archive.
Thank you.
Okay. Other question? Comments? Okay. If not, we thank again Professor Ascher for his interesting talk. And we see for the next talk on June 18 with Dr. Lorenzo Barzotti. Okay, good evening to everybody, and many thanks for your attention. Thank you again, Professor Ascher.
Thank you.